Good morning to all. In the previous lecture, we discussed the what is the self-adjoint. Okay, what is the self-adjoint operator and some theorems on it. Okay, so in this lecture, we will discuss what is the unitary operator and normal operator. Okay, so in this lecture, we discuss the two types of operator. Which one? Unitary operator and normal operator. Okay, first see the definition of unitary operator. Okay, what is the unitary operator? If A is the matrix of T with respect to ordered basis beta, then the matrix A, okay, the transpose of com the transpose of conjugate of A is equal to A inverse. If this condition satisfies, then the operator, the linear operator T is unitary operator. Okay. If the transpose of conjugate of A is equal to A inverse, then the matrix A is unitary matrix and the corresponding linear operator is unitary operator. Okay, look at the definition. In other words, T is unitary operator on an inner product space V if T is invertible and it preserves the inner product. Okay. In other words, T is unitary operator on an inner product space V if T is invertible and T preserve inner product. Okay. This is the definition of unitary operator. Okay. Look at this theorem. Let T be a linear operator and on inner product space V. Then T is unitary if and only if the adjoint T star of T exists and T into T star is equal to I, which is equal to T star into T. Okay. Look at the theorem once again. What is the statement is given to us? Let T be a linear operator on an inner product space V. Then T is unitary if and only if the adjoint of T star of T exists and T into T star is equal to I, which is equal to T star into T. If this condition holds, then we can say that T is unitary operator. Okay. In the proof, we assume first T is unitary operator, then we have to prove T into T star is equal to I, which is equal to T star into T. And in the second part, assuming the this part T into T star, which is equal to I, which is equal to T star into T, then we are going to prove T is unitary operator. Okay, look at the proof. Let T be a linear operator on an inner product space V. Okay, let T be a linear operator on an inner product space V. Suppose we assuming first T is unitary matrix. Okay, sorry, T is unitary operator. Then what is the definition of unitary operator? Then T is invertible, that is, there exists a linear operator T inverse on V such that T into T inverse is equal to I, which is equal to T inverse into T. Give it as equation number 1. And also T preserves what? Here, look at here. T is invertible and T preaches inner product. So what is the definition of inner product? And T inner product of T alpha T beta is equal to inner product of alpha beta. Okay, for all alpha beta belongs to V. So this is the definition of inner product. Okay, inner product preserves. It preserves the inner product. Okay, for all alpha beta belongs to V, give it as equation number 2. So what we have to prove? to prove that T possesses adjoint. Okay, and T into T star is equal to I is equal to T star into T. For all alpha beta belongs to V, we have to now consider, we have to prove this one. T into T star is equal to I, which is equal to T star into T. Okay, for this one, let us suppose for all alpha beta belongs to V, we consider CODR. It means consider inner product of T alpha with beta is equal to inner product of T alpha, and instead of beta we can write I of beta. Okay, identity operator. Okay, I of beta is nothing but beta. Okay, which is equal to inner product of T alpha and the inner operator I, we can write like this: T into T inverse. Why? Because T is invertible, and T into T inverse, which is equal to I of beta, from equation 1. Where is the equation 1? Look at it. This is the equation number 1. Okay, which is equal to inner product of T alpha and T of T inverse of beta. Okay, which is equal to T of alpha and T into T inverse of beta. Okay, hence the right hand side inner product of T of alpha and beta is equal to alpha, inner product of alpha and T inverse of beta from 2, because T preserves the inner product. From 2 we can write like this: inner product of T alpha T beta is equal to inner product of alpha beta, for all alpha beta belongs to V. Instead of beta here, T inverse beta is there. Okay, so T inverse beta as it is. Okay, because T preserves the inner product from equation number 2. Hence, inner product of T alpha beta is equal to inner product of alpha and T inverse beta. Thus, for the linear operator T on V, there exists a linear operator T inverse. This equation, our above equation implies that there exists a linear operator T inverse on V such that inner product of T alpha and beta is equal to inner product of alpha and T inverse of beta, for all alpha beta belongs to V. Okay, we get inner product of T alpha beta is equal to inner product of alpha with T inverse of beta, for all alpha beta belongs to V. Okay, what this shows that? This shows that the T possesses adjoint, the T inverse. Okay, T possesses adjoint T inverse. But by the definition of adjoint, adjoint of T is given by T star. Okay, but we discussed in the previous lecture, the adjoint of T is T star. Okay, but by the definition of adjoint, adjoint of T is given by T star, and hence by uniqueness, okay, the T star must be unique. Okay, the adjoint of any linear operator is unique. Hence, we have that T star is nothing but T inverse. Okay, so hence we get T into T star, which is equal to T into T inverse, which is equal to I, which is equal to T inverse into T, from equation number 1. What is the equation number 1? Look at here. Okay, instead of in T inverse, we have T star. Hence, the T into T inverse T star is equal to I in is equal to T star into T. Okay. So now look at the second part of the theorem. Conversely, we assume that T possesses adjoint T star. Okay, if in this case we considered as T possesses adjoint T star and T into T star, which is equal to I, which is equal to T star into T. Okay, but T into T star, which is equal to I, which is equal to T star into T, is implies that T star is the inverse of T. Okay, T into any operator is equal to I. It means that that operator must be inverse of T. Hence, here the T star is the inverse of T by the definition of invertible operator. Hence, T inverse is equal to T star. Therefore, T is invertible. Okay. Here we prove that T is invertible. Now we have to prove that the T preserves the inner product. Okay, we have to prove that if T preserves the inner product, then the T must be what? Unitary operator. Okay, in order to prove that T is unitary, it remains to prove that T preserves the inner product for all alpha beta belongs to V. Okay, for all alpha beta belongs to V. Now consider for this one, inner product of T alpha T beta is equal to inner product of alpha into T star into T of beta by the definition of adjoint operator. Okay, which is equal to inner product of T alpha and T beta is equal to inner product of alpha and T star of T of beta. Okay, which is equal to inner product of alpha, but T star into T is equal to I. Okay, from the above equation. Okay, here. Okay, so T star into T is equal to I of beta here, which is equal to inner product of alpha and I of beta. Okay, hence we get inner product of T alpha T beta is equal to inner product of alpha beta, since I of beta is equal to beta. Hence, this is true for all alpha beta belongs to V. Okay. Hence, this shows that T preserves the inner product. Okay. Hence, here we get T is the preserves the inner product, and here T is invertible. Hence, we can say that by the definition of unitary operator, here T is the unitary operator if T is invertible and T preserves inner product. Hence, we get here Hence, we get here T is unitary operator. Okay, understood? Okay, observe this all these steps. Okay, observe. Okay, so the next theorem is next one note is there. The product of two or more unitary operator is always unitary operator. Okay, if you take the two or more than two operators are unitary, then the product of two unitary operator is always unitary. The inverse of unitary operator is unitary. Okay, if inverse is also exist and this inverse of the unitary operator is always unitary operator. Okay, and third one is a linear operator T on an finite dimensional inner product space V is unitary if and only if T preserves the inner product. Okay, on an finite dimensional product, okay, inner product space, if V is the finite dimensional, then the operator T is unitary if and only if T preserves the inner product. So here there is no need to prove it that there is no need to prove T is invertible. Okay. So this is the definition and one theorem about unitary operator. Okay. So the next operator is normal operator. Okay, look at what is the definition of normal operator. Okay, let V be a finite dimensional inner product space and T be the linear operator on V. We say that T is a normal operator if it commutes with its adjoint. Okay, let V be the finite dimensional inner product space and T be linear operator on V. We say that T is normal operator if it commutes with its adjoint. That is, T into T star is equal to T star into T. Okay, only T into T star is equal to T star into T. If it is equal to I, then it is called as unitary operator. But here, not equal to I. It may be or may not be. Okay, if T into T star is equal to T star into T, then the T is called normal operator. Okay, look at some notes is there. First one, any self-adjoint operator is normal operator. Okay, any self-adjoint operator is normal operator. How? Look at here. Suppose T is self-adjoint. Then, by the definition of self-adjoint, we can write like this. T star is equal to T. Okay, T star is equal to T. Now consider T into T star is nothing but put T as it is, and instead of T star, we can write here T. Okay, which is equal to. So here in the left side, okay, put T star instead of T and T as it is here. Okay, hence we get T into T star is equal to T star into T. Hence T is normal operator. So any adjoint operator is normal operator. Okay, so this is the proof of the above statement. Now the second statement. Any scalar multiple of normal operator is normal. Okay, any scalar multiple of normal operator is normal. Look at the proof. Suppose T is normal, then we have T into T star is equal to T star into T. Okay, now we have to assume any scalar multiple of normal operator T. Let that becomes S, which is equal to C into T. So any scalar multiple of T. Okay, be the scalar multiple of T. We want to prove that S into S star is equal to S star into S. Okay, for this one, we consider the left hand side S into S star, which is equal to what is the value of S? C into T. What is the value of S star? C into T bracket star. Okay, C into T bracket star, which is equal to C into T, but C bar into T star. Okay, C into 2 bracket star, we can write like this, C bar into T star, which is equal to C as it is, put T in the bracket, T into C bar into T star. Okay, so which is equal to C into C bar, which is equal to T into T star. But T into T star is nothing but T star into T. Hence, which is equal to C into C bar is equal to T star into T. Okay. Now consider again S star into S, this product, which is equal to C into T bracket star, which is equal to C into T, putting the value of S star and S here, which is equal to here C T bracket star, which is nothing but C bar into T star. and c into t as it is there. Okay, which is equal to c bar as it is. Okay, now t star of ct. Here the c comes as a outside. Okay, okay. So what we have? C bar of bar. Okay, which is equal to t star into t, which is equal to c into c bar, which is equal to t into t star, because t star into t is equal to t into t star. So here we get c into c bar is equal to t into t star into t into t star. Here c is there, not c double bar. Okay, c bar into c. Okay, so at the end, c into c bar is equal to t into t star. Hence, the s into s star, the value of s into s star and s star into s must be equal. Hence, we get any scalar multiple of normal operator is normal. Okay, third theorem. Sum and product of normal operator need not be normal. Okay, here sum and product of normal operator need not be normal. Okay, for this one we have no need to prove the third statement. Okay, now the next point is theorem. Let V be an inner product space and T be the self adjoint operator on V. Okay, let V be an inner product space N and T be the self-adjoint operator on V, then each characteristic value is real. Each characteristic value is real and characteristic vector associated with distinct characteristic values are orthogonal. Okay, here we given that here they given to us t be the self-adjoint operator. Okay, and each characteristic value is real and characteristic vector associated with distinct characteristic values are orthogonal. We have to prove. Okay, all the characteristic values are real and t is self-adjoint. They are given to us. Okay, so what we have to prove? Each characteristic value is real and characteristic vector associated with distinct characteristic values are orthogonal. Proof. Let T be a self-adjoint operator on V. Okay. We have given to us, they have given to us T be the self-adjoint operator on V. Thus, it implies that T star is equal to T. Give it as equation number 1. Let C be the any characteristic value of T. Okay. Then there exists a non-zero vector alpha belongs to V such that T of alpha is equal to C alpha. Give it as equation number 2. By the definition of characteristic vector, we can write like this. T of alpha is equal to C into alpha. Now we have to prove that the C is real. That is, we have to prove that C bar is equal to C. Okay. If, if C bar is equal to C is nothing but C is real, any real number. Okay. For this one, if we have to prove this C is real, that is true, we have to prove that C bar is equal to C. For this, consider C into inner product of alpha alpha, which is equal to inner product of C alpha into alpha. Okay, by linearity property of inner product space, which is equal to C alpha is nothing but T of alpha from 2, inner product of T alpha alpha, which is equal to inner product of alpha and T star of alpha by the definition of adjoint. Okay, which is equal to inner product of alpha and T of alpha, because T star is equal to T, so instead of T star we can write T. which is given to us, okay, which is equal to inner product of alpha and C of alpha, because T of alpha, value of T of alpha is C of alpha, okay, which is equal to C bar of alpha alpha by again linearity property of inner product. Here the left hand side C into alpha alpha, which is equal to C bar into alpha alpha, inner product of alpha alpha. Taking to the left side, we get C into inner product of alpha alpha minus C bar into inner product of alpha alpha is equal to 0. Okay, which is equal to C minus C bar into inner product of alpha and alpha is equal to 0. But here the alpha is not equal to 0. Okay, hence we get C minus C bar must be equal to 0, which is equal to C bar is equal to C. It means that C is the real number. But what is the value C? It is the characteristic value of T. Okay, so any characteristic value of self-adjoint operator is real, which shows that every characteristic value of a self-adjoint operator is real. Give it as equation number star. Okay, let alpha be any other characteristic value of t such that d which is not equal to c, that is c minus d is not equal to d. Give it as equation number 3. Thus, there exists a non-zero vector beta belongs to V such that T of beta is equal to d beta. Give it as equation number 4. To prove that alpha, inner product of alpha and beta must be equal to 0. Okay, beta is the any other value other than C, characteristic value. Okay, so we have to prove that that sorry, beta is the any other characteristic vector. Okay, beta be the any other characteristic vector associated with characteristic value d. Okay, we have to do that the alpha and beta, inner product of alpha and beta is equal to 0. Consider C into inner product of alpha beta, which is equal to inner product of C alpha and beta by linearity property of inner product, which is equal to, but C of alpha is equal to T alpha. So inner product of T alpha and beta from equation number 2, which is equal to inner product of alpha and T star of beta by definition of adjoint operator. Okay, which is equal to inner product of alpha and T of beta from 1, because T star is the self-adjoint. It means that T is the self-adjoint. It means that T star is equal to T. Okay, which is equal to inner product of alpha and d beta. Why d beta? Because T of beta is equal to d beta here from equation number 4. Okay, which is equal to d bar into inner product of alpha beta by linearity property of second property. Okay, second variable. D bar is here second variable. Na? So here comes as a D bar into inner product of alpha and beta. Okay, which is equal to C into inner product of alpha beta is equal to D into inner product of alpha beta. Taking to the left hand side, we get C into inner product of alpha beta minus D bar into inner product of alpha beta is equal to 0 from equation number star here. Where is the star? Here. Okay, from star. Equation number 3. Hence we get, but from 3 we have C minus D is not equal to 0, because these are two distinct characteristic values. Hence from equation 5 we get alpha and beta. The inner product of alpha and beta must be equal to 0. Okay. What this shows that? This shows that alpha is the characteristic vector. Okay, alpha is the characteristic vector associated with eigenvalue or characteristic value C, and beta is the eigenvector or characteristic vector associated with characteristic value D. Then the inner product of these two vectors must be 0. It means that the characteristic vector, it shows that the characteristic vector associated with distinct characteristic value are orthogonal. Okay, this is the proof of the theorem. Okay, so observe this all these steps. Okay, okay, so this is the proof of the theorem. Let V be the inner product space and T be the self-adjoint operator on V. Then each characteristic value is real and characteristic vector associated with distinct characteristic values are orthogonal. This is the proof of the theorem. Okay. So the next point is that one more theorem is there. Okay. What says the theorem? Let V be the finite dimensional inner product space. Suppose W is the subspace of V, which is invariant under T. Then the orthogonal complement of W is invariant under T star. Okay, here given us W is invariant under T, which is the subspace of V. Okay, then orthogonal complement of W, that is W per, it's invariant under T star. So we have to show that taking T of W is contained in W, we have to show T of W per is contained in W per. Okay, let's see the proof later. Let T be the linear operator on finite dimensional inner product space V. Let T be a linear operator on an finite dimensional inner product space V. Then T possesses adjoint T star. Then T possesses adjoint T star. Suppose W is the subspace of V, which is invariant under T. What it means? T of W is contained in W. So this is the definition of invariant under T. Okay, that is for if you take an alpha belongs to W, it implies that T of alpha belongs to W. Okay, now look at this. Let W per be the orthogonal complement of W. Okay, we have assumed that W per is the orthogonal complement of W. So by the definition of W per, which is equal to take alpha belongs to V such that inner product of alpha beta is equal to 0 for all beta belongs to W. Okay, so this is the definition of W per. So we have to prove that W per is invariant under T star. That is to prove that T star of W per is contained in W per. For this, we take an element from W per and the image of that T of alpha belongs to W per. Okay, look at here. Let alpha belongs to W per be any vector taken from W per. Okay, then by the definition of W per, the inner product of alpha and beta is equal to 0 for all beta belongs to W by the definition of W per. Okay, orthogonal complement. But beta belongs to W, which implies that T of beta also belongs to W because W is invariant under T. Okay, hence the equation 2 becomes inner product of alpha. Instead of beta, we can write T of beta. Why? Because beta belongs to W, for all beta belongs to W. So taking any element from W, We have taken here t of beta. Okay, t of beta which is equal to 0 for all beta belongs to W. Okay, by the definition of adjoint, which is implies that t star of alpha, inner product of t star alpha and beta is equal to 0 for all beta belongs to W. Okay, so this is the definition of adjoint. Then, by the definition of orthogonal complement, T star of alpha belongs to W one. But this is the definition of, by the definition of orthogonal complement, we can say that T star of alpha belongs to W per. Okay. Thus, here we taken at the starting alpha belongs to W per, which implies T star of alpha belongs to W per. It means that T star of W per is contained in W per. That is, W per is invariant under T star. Okay, so this is the proof of the theorem. Look at the theorem. What this is, if V is the finite dimensional inner product space, suppose W is the subspace of V, which is invariant under T, then orthogonal complement of W is invariant under T star. Okay, so this is the theorem and proof. Okay, so next theorem is this one. Let V be the finite dimensional inner product space and T be a normal operator on V. Then alpha is characteristic value of T, characteristic vector of T with characteristic value C if and only if alpha is characteristic vector of T star with characteristic value C bar. Okay, what we have? T be the normal operator. We given here given as T be the normal operator on V. Then we have to prove that alpha is the characteristic value of T, characteristic vector of T. Okay, alpha is the characteristic vector of T with characteristic value C if and only if alpha is characteristic vector of T star with characteristic value C bar. Okay, look at the proof. Let T be the normal operator on an finite dimensional inner product space V. Then, by the definition of normal operator, T into T star is equal to T star into T. Give it as equation number 1. For any alpha belongs to V, consider norm square of T alpha is equal to inner product of T alpha and T alpha by the definition of norm, which is equal to, by the definition of adjoint, we can write inner product of alpha and T star of T of alpha. Okay, which is equal to alpha into inner product of alpha T star T of alpha. Okay, but T star of T is nothing but T into T star. Hence, we get inner product of alpha and T into T star of alpha from equation number 1. Okay, hence we get, by the definition of adjoint, this T. So this T moves towards the alpha, then we get T star of alpha and T star of alpha, which is equal to, the definition of norm of T star, hence norm square of T star alpha for all alpha belongs to V. Hence we have norm square of T alpha is equal to norm square of T star alpha, which is equal to norm of T alpha is equal to norm of T star alpha for all alpha belongs to V. Give it as equation number 2. Okay, this shows that if T is normal, then T alpha, norm of T alpha and norm of T star alpha both are equal for all alpha belongs to V. Give it as equation number 3. Now for any scalar C, for any scalar C, T minus C alpha is linear operator on finite dimensional inner product space V. Okay, hence it possesses the adjoint. t minus c I t minus ci bracket star. Okay, t minus ci is the linear operator on a finite dimensional vector space, inner product space V. Okay, hence it possesses adjoint t minus ci bracket star. Hence t minus ci bracket star is equal to t star into ci bracket star, which is equal to t star minus taken c as bar, c bar into I star, but I star is equal to I, which is equal to t star minus c bar I. Okay, now we have to claim that T minus Ci is normal. For this normal, we have to show this is normal. So consider T minus Ci into T minus Ci bracket star, which is equal to T minus Ci into T star minus C bar into I. By doing multiplication, we get T into T star minus C bar into T star minus C into T star plus C into C bar. Give it as equation number 4. Now assume this one T minus Ci bracket star, which is into T minus Ci, which is equal to T star minus C bar I into T minus Ci. Okay. By solving this one, we get t star into t minus c into t star minus c bar into t plus c into c bar. We have to solve this one. Okay. So at the end, we get t into t star minus c bar into t minus ct into c into c bar. Give it as equation number 5. So from equation 4 and 5, the both are right hand side equal, then left hand side must be equal. Okay, so t minus ci into t minus ci star bar is equal to t minus ci bracket star into t minus ci. Thus, by the definition of operator, normal operator, t minus ci is normal. Okay, hence we get from the equation number 3, we have norm of t minus ci of alpha, which is equal to norm of t minus ci bracket star alpha, for all alpha belongs to V, which shows that norm of t minus ci into alpha, which is equal to norm of t star minus c bar I alpha, for all alpha belongs to V. Okay, hence it implies that t minus ci of alpha is equal to 0 if and only if t star minus c bar I of alpha is equal to 0, for all alpha belongs to V. That is, T of alpha is equal to C alpha if and only if T star of alpha is equal to C bar of alpha, for all alpha belongs to V. Hence, this shows that alpha is the characteristic vector of T with characteristic value C if and only if alpha is the characteristic vector of T star with characteristic value C bar. Okay, so this is the definition. Okay, this is the theorem and proof of the above theorem. Okay, what says the theorem? If V is the finite dimensional inner product space and T be the normal operator on V, then alpha is characteristic vector of T with characteristic value C if and only if alpha is the characteristic vector of T star with characteristic value C bar. Okay, so in the next lecture, in the next video, we will see the unit number 5. Okay, thank you.